Chapter 21 problems. Problem number 1. A container having a volume of 1 cubic meter holds 5 moles of helium gas at 50 degrees centigrade. If the helium behaves like an ideal gas, the total energy of the system is... Right, so we have a ideal gas. It's helium gas. We have 5 moles of it. So we'll say helium gas. Now, helium is a monatomic gas. It does not have the vibrational modes, and so it does not have another way of storing energy. It's just purely translational. So for a monatomic gas, we have that the energy is equal to 3/2 number of moles times the gas constant times the temperature. It's 3/2 because we get 1/2 for every degree of freedom, and for a monatomic gas we have 3 dimensions to deal with. We have degrees x, y, and z. So we have 1/2 for each, so we get 3/2. Now, when I use this formula, I have 2 possibilities for the gas constant here. And it really depends on the other variables that are given in the problem. In particular, R is equal to 8.31 if the pressure is given in terms of pascals, which is newtons per meter squared, and the volume is given in terms of cubic meters. So this would give us joules per mole per degree Kelvin. And we'll use this if the pressure is in newtons per meter squared, or pascals, and the volume is in cubic meters. That will give us joules per mole per degree Kelvin. We'll use this gas constant. The other possibility is that we'll have 0.0821, and this will be atmospheres, liters per mole per degree Kelvin. And we'll use this if the pressure is given in atmospheres and the volume is in liters. So if you're given a problem, the pressure is given in atmospheres, the volume is given in liters, use this gas constant for all these kinds of problems. So in this particular case, we were given that the volume was 1 cubic meter. Ultimately, we were asked for the energy, and the answer is given in joules. So and we're given moles and degrees Kelvin, so we can go directly with this gas constant right here. All right, so we have E was 3/2 nRT, which would be 3/2. We had 5 moles, 8.31. The temperature was given as 50 degrees centigrade. Now for all these formulas, we better make sure that all of our temperatures are in Kelvin. So we need to convert that 50 degrees, let's put it up here, 50 degrees centigrade is equal to 50 plus 273.15, or 323.15 Kelvin. Now, so we're going to use that down here. And when I multiply all those out, I get 2.01 times 10 to the 4 joules. And so that is the energy of 5 moles of our ideal gas. I'll note that the volume of 1 cubic meter that was given in the problem is extraneous information. To solve this, we didn't need to know that volume. Problem number 2. A container having a volume of 1 cubic meter holds 5 moles of helium gas at 50 degrees centigrade. If the helium behaves like an ideal gas, the average kinetic energy per molecule is... Well, this is like the last problem. I mean, exactly the same setup. We have 5 moles of an ideal monatomic gas, helium, and now for per molecule, it doesn't matter. Well, it does matter whether it's monatomic, but it doesn't matter whether it was helium and what the volume was. Per molecule, we have an energy, kinetic energy, of 3/2 Boltzmann constant times the temperature. And again, the 3/2 is for the 3 degrees of freedom. So we really have 1/2 Boltzmann constant times temperature per degree of freedom. And since monatomic, we have 3 degrees of freedom. If it were diatomic, say, then we'd have 5 degrees of freedom. We'd have to worry about that. In this case, then, we have 3/2. The Boltzmann constant is 1.38 times 10 to the minus 23. And again, we have the same temperature as in the last problem, 323.15. This constant is actually the R constant divided by Avogadro's number. So it's R divided by 6.02 times 10 to the 23. And that's how we get the Boltzmann constant. But it's a universal constant we can find in front cover of any physics book. This gives us 6.69 times 10 to the minus 21 joules. That would be per molecule. So that's our answer. Problem number 3. The average kinetic energy of a nitrogen molecule at room temperature, 20 degrees centigrade, is. Now this is a nitrogen molecule, which nitrogen in its preferred state has the form of N2, which means it's a diatomic molecule. So it has not only the 3 degrees of translational freedom, but it also has vibrational freedom as well. And it's 2 modes of that. So instead of 3/2, instead of 3 degrees of freedom, we have 5 degrees of freedom. And so for a nitrogen molecule, the kinetic energy would be 5/2 K Boltzmann times the temperature. And so this would be 2.5 times 1.38 times 10 to the minus 23. Same temperature. And, oh, no, not the same temperature. Okay. We have at 20 degrees centigrade, not 50. So that would be 293.15. And when we put those numbers in, we get 1.01 times 10 to the minus 20 joules. So that is the average kinetic energy of a nitrogen molecule, a diatomic molecule, at room temperature, 20 degrees centigrade.
Good.
Problem number 4. The average translational speed of a nitrogen molecule at room temperature, 20 degrees centigrade, is approximately in meters per second. What? Well, we actually have a formula for the average translational speed, the RMS speed for a molecule, and that's equal to 3RT over the molecular mass, molecular weight of the molecule, square root. So in this case, we have 3 times our gas constant, 8.31. This is at 20 degrees centigrade, so it's going to be 293 degrees Kelvin, or 293.15 to be exact. Over the molecular weight of nitrogen. Now, what is the molecular weight of nitrogen? Nitrogen is a diatomic molecule, N2, and there's for nitrogen itself on the periodic table, it's got the atomic number of 7, which means its nuclear number is 14, and as a diatomic molecule, then it would have 28. So it's 28 grams per mole. If you had 28 grams of nitrogen, you would have a mole of nitrogen. Now, we want that in the SI system, so we'll say that the molecular weight of nitrogen is actually 28 times 10 to the minus 3 kilograms per mole. Right, so that's the molecular weight that goes in there. 28 times 10 to the minus 3. There's just a little sideline here. So our V, I could have put an RMS on this. Our root mean square velocity is all this. And what is all that? That is 510 meters per second. So that's our answer. Problem number 5. Assume 3 moles of a diatomic gas has an internal energy of 10 kilojoules. Determine the temperature of the gas after it has reached equilibrium. All right. Well, we have 3 moles of a diatomic gas. Now, for diatomic gas, the energy is 5/2 nRT because we have those extra 2 degrees of freedom. So our fraction is 5/2 instead of 3/2. And we have 3 moles, and we're given the total energy. So we're given the energy, we know the number of moles, we know R's constant, so we'll solve this for temperature. So temperature will equal 2/5 times the energy divided by the number of moles times the R constant. 2 times 10,000 joules over 5 times the number of moles, 3 times 8.31. And this gives us, temperature should come out in Kelvin since that's our basic unit. And this comes out to 160.4 Kelvin. A 50-gram sample of dry ice, which is solid carbon dioxide, is placed in a 4-liter container. The system is sealed and allowed to reach room temperature at 20 degrees centigrade. By approximately how much does the pressure inside the container increase when the dry ice turns to gas? Ignore the initial volume of the sample. All right, so we're going to have some kind of container. We're going to put 50 grams of solid dry ice, carbon dioxide, into this container. It's going to turn into gas, and by turning into gas, it's going to add pressure to the system. Now, we don't know what gas was originally in that container, and hence we don't know how much of the ambient gas was in there and how much pressure that was adding to the container itself to begin with. However, the question is, how much does the pressure increase due to the CO2? So it doesn't really matter what the initial pressure was because we're going to look at the extra pressure added by this carbon dioxide. So we have 50 grams of carbon dioxide, CO2 dry ice. What we really need to know then is how many moles does this represent? Because then we can figure out the pressure due to that number of moles of gas when it all turns to gas at the precise temperature and at the volume that we're considering, which is 4 liters. So our volume is 4 liters. Our temperature is 20 degrees centigrade, which would be 293.15 Kelvin. And if we knew N, then we can solve this because we know from the ideal gas law that PV equals nRT. So the pressure we're looking at is going to be nRT divided by V. And we know V and T. If we knew N, we could do it because we know R. R is going to be, it looks like we're going to be using, since volume is given in liters, we're going to be using that second version of R, which is 0.0821 atmospheres, liters per mole per degree Kelvin. So we'll be using this one. Okay, so we need to find N. Now we know we have 50 grams of carbon dioxide. And what is the molecular weight of carbon dioxide? Well, the atomic weight of carbon is 12 grams per mole, and the atomic weight of oxygen is 16. So for CO2, that would be two oxygens plus a carbon, which would be 32 plus 12 is 44 grams per mole, which is the same as 44 times 10 to the minus 3 kilograms per mole.
Hold on one second. Hey, can we get a pause just for a second?
So we have 44 grams per mole, and what we really wanted to find was how many moles did we have. Now we have 50 grams, and there's 44 grams per mole, so we could just say that the number of moles we have, if there's, would be the actual mass that we have divided by the mass per mole, molecular weight, which would be 50 grams divided by 44 grams per mole. And that gives us a number of moles of 1.136. That's our N for this formula here. So now we can find the extra pressure added by the CO2. Equals nRT divided by V. So this would be 1.136 moles times our gas constant, and we want to use this one, 0.0821. Temperature was 293.15, and volume was 4 liters. So everything's in the right units for that gas constant, and this gives us an answer of 6.835 atmospheres. And I guess the answer is increases by about 7 atmospheres. Problem number 7. According to kinetic theory, a typical gas molecule in thermal equilibrium at room temperature has a kinetic energy of K equal to 6 times 10 to the minus 21 joules, regardless of mass. Estimate the speed at room temperature of a hydrogen molecule, which has a mass of 3.34 times 10 to the minus 27 kilograms, and a xenon atom, 2 times 10 to the minus 25 kilograms, if our K Boltzmann is 1.38 times 10 to the minus 23 joules per Kelvin.
Good.
Let's do this. We're told that the average kinetic energy, regardless of mass, is about 6 times 10 to the minus 21 joule. So let's just say, that our average kinetic energy, 1/2 mv squared, equals K, this value. Now let's solve this for the velocity. So multiply both sides by 2, divide by the mass. So the velocity will equal 2 times the kinetic energy divided by the mass, square root. And so that's our formula. If we did this for hydrogen, then we'd say that the average speed of hydrogen would be equal to 2 times this kinetic energy, 6 times 10 to the minus 21, over the mass given for hydrogen, a hydrogen molecule, which would be 2 hydrogen atoms, which is 3.34 times 10 to the minus 27 kilograms. Everything's SI system. So that gives us a average speed of 1,896 meters per second for hydrogen. We also want to do the same thing for xenon. So we'll look at xenon. We have velocity should equal square root 2 times kinetic energy over the mass, 2 times 6 times 10 to the minus 21 kilograms, or the mass of xenon, which was given as 2 times 10 to the minus 25 gives us 245 meters per second. Hydrogen's a lot faster than xenon, which is one reason why hydrogen has a tendency to escape the atmosphere, because it's got more velocity. Problem number 8. The air in an automobile engine at 20 degrees centigrade is compressed from an initial pressure of 1 atmosphere and a volume of 200 cubic centimeters to a volume of 20 cubic centimeters. Find the temperature if the air behaves like an ideal gas with a gamma constant of 1.4 and the compression is adiabatic. Okay, so we have an ideal gas, but we're told that this compression is adiabatic, and for adiabatic compressions we can say this, that the initial temperature times the initial volume times the gas constant, the gamma gas constant, which depends on whether the gas is monatomic or diatomic. If it's diatomic, generally our gamma is going to be 1.6, monatomic will be 1.67, diatomic will be 1.4. So it depends on the gas, and this is equal to a constant, so we have this. For an adiabatic compression. Not only that formula, but we also have this one. And I think there was another one I derived in your notes, but let's just keep these for the moment. So we're going to assume that this automobile engine has an adiabatic compression. In fact, that's what's normally assumed for the Carnot cycle in a gasoline engine. So let's write down what we know on this one. We're going to start at 20 degrees centigrade. So our T initial is 20 degrees centigrade, or 293.15 Kelvin. We're told that our initial volume for the cylinder is 200 cubic centimeters, and our final volume is 20 cubic centimeters. I'm going to keep those in those units because we're going to do a ratio of the volumes anyway, so the units are going to cancel out. So normally I probably would change that into cubic meters, but we don't need to do that. We want to find the final temperature after this compression. So let's use this formula up here, and we'll say that T final is equal to T initial times the initial volume, gamma minus 1, over the final volume, gamma minus 1. Just taking this and bringing it over there, which I could write as T initial times the initial volume over the final volume to the gamma minus 1. Let's put in our numbers. T initial is 293.15. The initial volume was 200, the final volume is 20. And the cubic centimeters cancel out, so this should just be 10 to the gamma minus 1. And gamma for, well, we're given the gamma. Gamma was given as 1.4. So we're assuming that this is probably mostly a diatomic type gas. So this would be 1.4 minus 1. And so that's going to be 293.15 times 10 to the 0.4 power. And that gives me 736.4 Kelvin. Now the answer was given in Celsius. We wanted to find the temperature in Celsius, so this is Kelvin. Temperature in Kelvin is equal to temperature in Celsius plus 273.15. So if we want the temperature in Celsius, we're going to have to subtract that 273.15. So this will be 736.4 minus 273.15 gives us 463.2. So that is the final temperature in Celsius after this compression, and that allows the gasoline to ignite and we get our power.
Good.
Problem number 9. During an adiabatic compression, the volume of air decreases to 1/4 its original size. Calculate its final pressure if its original pressure was 1 atmosphere. Assume the air behaves like an ideal gas with gamma equal to 1.4. All right, so we have another adiabatic compression, and so we have the same kinds of formulas, and this time we're told a relationship involving the pressure, so we want the pressure, and we're also told the volume decreases as well, so we want the pressure and the volume in our formula. So we have P initial, volume initial to the gamma equals P final, volume final to the gamma constant. That's our relationship for the adiabatic compression where the pressure changes. And in this particular case, it says the volume of air decreases to 1/4 its original size. So our V final will equal 1/4 our V initial. Also, we're told that it's an ideal gas with gamma equal to 1.4. Calculates final pressure if its original pressure was 1 atmosphere. So P initial is 1 atmosphere. There's all of our information, so let's find the final pressure. The final pressure will equal the initial pressure times V initial to the gamma divided by V final to the gamma. Just rearranging this equation up here. And so that's equal to the initial pressure times V initial over V final to the gamma power. Well, our initial pressure is 1. Our V final is equal to 1/4 our V initial, so let's put that in there. And our gamma is 1.4. These V initials cancel out, so we have 1 over 1/4, which will just be 4. So this will be 4 to the 1.4 power, and that gives me 6.96. Everything was given in atmospheres. That's 6.96 atmospheres. Problem number 10. An ideal gas is allowed to expand adiabatically until its volume increases by 50%. By approximately what factor is the pressure reduced? All right, so another adiabatic gas problem. And what is mentioned in the problem is the volume being reduced, expanded, and the pressure being reduced. So it's pressure and volume involved. So we're going to use the same formula as we did in the last problem. We have P initial, V initial to the gamma equals P final, V final to the gamma. Now what do we know? Let's see what was given. We know that the gamma was given as 5/3. So our gamma is 5/3, which is 1.67. So this must be a monatomic gas, even though it wasn't stated as such. It says it expands adiabatically until its volume increases by 50%. So V final is going to equal 3/2 V initial. In other words, 50% more of V initial. And that's it. Now we want to see approximately what factor is the pressure reduced. So let's get a ratio of the final pressure to the initial pressure. Divide both sides by P initial, bring V final over here. So we have P final over P initial will equal V initial to the gamma divided by V final to the gamma. Just rearranging this original equation up here. So that's going to be V initial divided by V final to the gamma power. So I'll say that my ratio of my final pressure to my initial pressure will equal the ratio of V initial, and V final was 3/2 V initial, and gamma is 1.67. V initials cancel out here, so this is going to be equal to 2/3 to the 1.67 power. And that gives me 0.512. Just a number, it's a ratio with no units on it. The question was, by approximately what factor is the pressure reduced? Now the final pressure is approximately 1/2 of the initial pressure. The factor then means it's reduced by approximately a factor of 2. So this might say that we are reduced by a factor of 2. And so we only have one answer for that. That would be answer B. Problem number 11. During the volcanic eruption of Mount Pelee in 1902, an incredibly hot, burning cloud rolled down the mountain and incinerated the town of St. Pierre. From the damage done, the temperature in the cloud was estimated at 700 degrees centigrade. If the air temperature was 20 degrees centigrade and the molecular weight of air is 29 grams per mole, estimate the molecular weight of the gas in this burning cloud that made it heavier than the surrounding air. As a follow-on, estimate the most probable composition of the cloud. Some typical volcanic gases are hydrogen sulfide, H2S, sulfur dioxide, SO2, sulfuric acid, H2SO4, carbon dioxide, CO2, and nitrogen oxide, NO. Okay. Well, for our root mean square velocity of the gases, we had this formula. Where m was the molecular weight of the gas. In this problem, we're going to assume that the gas and the dangerous cloud had the same root mean square velocity. So we'll say the RMS for the air is the same as the RMS for the gas, for the cloud. So I could write this as 3R temperature of the air over the molecular weight of air square root equals 3R temperature of the cloud over the molecular weight of the cloud square root. Let's square both sides, so get rid of the square roots, and let's divide by 3R on both sides, so we'll get rid of the 3R's. And so we'll have the temperature of the air to the molecular weight of air equals the temperature of the cloud to the molecular weight of the cloud. Now we know the temperature of the air, that was 20 degrees centigrade. Of course we're going to change this to Kelvin because that's the only way we can do these kind of ratios and stuff. We need to be in the absolute temperature scale. So our temperature of the air, which is 20 degrees centigrade, will be 293.15 degrees Kelvin. The temperature of the cloud was 700 degrees centigrade, plus 273 will give us 973.15 degrees Kelvin. We're told that the molecular weight of air is 29 grams per mole. And so we want to find the molecular weight of the cloud. So let's just rearrange this algebraically. Molecular weight of the cloud is going to be equal to the molecular weight of air times the temperature of the cloud over the temperature of the air. This is going to be 29 times 973.15 over 293.15. And that gives us an answer of 96.3. I guess it would be grams per mole for the molecular weight of this cloud of gas. Now we look at our options for the components of volcanic gases. We have hydrogen sulfide, and H of course has an atomic weight of 1, so we got 1 plus 1, and sulfur has a molecular weight of 14, or atomic weight of 14. So this will give us a molecular weight of 16 for that. We have SO2. We have a 14 plus 16 plus 16, which would be 32, 46. Not quite yet. We have CO2, which would be 12 plus 16 plus 16, which would be 44 grams per mole. No, that doesn't work. We have nitrogen oxide. Oops, I think I got the sulfur wrong. So better check on that because nitrogen is 14. And that would be 30. I think sulfur is actually 32. So this would be 64. Still not good enough. And we have H2SO4. And we have 1, 2, 2 from the hydrogen, 32 from the sulfur, and we have 32, 64 from the 4 oxygens, because we have 16 plus 16 plus 16 plus 16. So that is 96, 98 grams per mole. We figured out that the molecular weight of this cloud is 96.3, and it's very likely that the majority of that cloud was actually comprised of H2SO4, sulfuric acid. That would not be much fun, especially also at 700 degrees centigrade. Problem number 12. 1 mole of helium gas expands adiabatically from 2 atmospheres pressure to 1 atmosphere pressure. If the original temperature of the gas is 20 degrees centigrade, what is the final temperature of the gas, given that our gas constant, or our gamma constant, is 1.67? All right, so in this problem number 12, we have an adiabatic, compression or expansion. Expands adiabatically from 2 atmospheres to 1 atmosphere. So the volume is increasing, but the pressure is going down. Now we're given the values of the pressure, and we're told the original temperature is 20 degrees. What is the final temperature? So we want a relationship that involves pressures and temperature. Now, we didn't have a formula for that. We had temperature initial, volume initial, gamma minus 1 equals temperature final, volume final, gamma minus 1. And we also had pressure initial, volume initial, gamma equals pressure final, volume final, gamma minus 1. We did not have a relationship that related temperature to pressure. Well, from this first formula here, we can say that our final temperature to our initial temperature is equal to our initial volume, the gamma minus 1, over our final volume, the gamma minus 1, which I could write as initial volume to final volume, gamma minus 1. All right, we'll deal with that first, like that. We can also say from, oh, I put a gamma minus 1 in there too. Should have been just gamma. We can also say from this second formula that P final over P initial will equal V initial to the gamma over V final to the gamma, which would be V initial over V final to the gamma, which I could write, I could say then that V initial to V final is equal to P final over P initial to the 1 over gamma, because I'm going to take the gamma root of both sides. So I can get this right here. And now I'm going to substitute this in there. So I'm going to have T final to T initial equals P final to P initial to the 1 over gamma, all that to the gamma minus 1. So I have a power times a power. Bear with me, we're going somewhere with this. T final, the T initial, is going to be P final to P initial to the gamma minus 1 divided by gamma, like that. We want to find the final temperature based on knowing the initial pressure, the final pressure, and initial temperature. So we're going to say that T final will equal T initial, P final over P initial, gamma minus 1 over gamma. And our initial values were P initial was 2 atmospheres, P final was 1 atmosphere, and T initial was 20 degrees centigrade, which would be 293.15 Kelvin. We don't have to worry about the fact that these units are in atmospheres for P, because again we have a ratio of atmospheres over atmospheres. Units will cancel out, so that'll just be a number. So it's the ratio that's important. And of course our gamma was given as 1.67, so it must be a monatomic gas. We'll put all those things in there. And now we have T final equals 293.15 times P final, which is 1, over P initial, which is 2, to the 1.67 minus 1 over 1.67. And if I do all that, this would be 293.15 times 0.5, and all that will be 0.67 over 1.67, which will be 0.401 power, and that gives me 222 degrees Kelvin. So that is our final temperature in this adiabatic expansion. Problem number 13. Air expands adiabatically, which means no heat in, no heat out, from temperature of 300 degrees Kelvin and a pressure of 100 atmospheres to a final pressure of 1 atmosphere. Treat the gas as ideal with a gamma of 1.4 and determine the final temperature. Compare your result to the boiling points of nitrogen, 77.4 degrees Kelvin, and oxygen, 90.2 degrees Kelvin. Could this method result in the liquefaction of air? Well, fortunately, in looking at this problem number 13, we worked on problem number 12. So we got a good result from 12. And again, this one is dealing with temperature and pressure. So from our result of 12, we got this right here. It's kind of nice one. So we have T final equals T initial, P final over P initial, gamma minus 1 over gamma. Probably not one of your regular formulas. You probably won't see this in your book, so it's just probably one that you can have around, possibly on your formula card. In this particular case, we're told that T initial 300 K. P initial is 100 atmospheres. P final is 1 atmosphere. And gamma was 1.4. So we're going to let it expand, and we're going to let the final pressure go to really small, and let this cool as a result. Let's see how much it will cool from room temperature. T final will equal room temperature, or 300 degrees Kelvin. P final is 1 atmosphere. P initial is 100. Again, the ratio, atmospheres to atmospheres, will cancel out, so it's just the ratio we want. Gamma was 1.4 minus 1 over 1.4. And this gives us, I'm going to write this like this. 1 over 100 is 10 to the minus 2. And all this stuff over here is 0.286. So it's going to be 0.4 divided by 1.4, which is 0.286. And negative 2 times all that will give me something that looks like this. Negative, I'm sorry, 0.571. That's something you can actually put in your calculator then. And this gives us 80.48 degrees Kelvin. So by putting this gas under these conditions, taking the large pressure, reducing the pressure, expanding it adiabatically so it's well insulated from the outside, we can cool this down to 80.5 degrees Kelvin, which is pretty cold. Not cold enough, cold enough to liquefy the oxygen, but not cold enough to liquefy the nitrogen, because nitrogen is liquid at 77 degrees Kelvin, not cold enough for that. So air is 20% oxygen and approximately 80% nitrogen. We would liquefy the air, but not the nitrogen. Not good enough to do it, to liquefy air. Problem number 14. The average molecular translational kinetic energy of a molecule in an ideal gas is. Well, this is the average translational kinetic energy. If we're only dealing with translational kinetic energy, we're only dealing with the 3 degrees of freedom, x, y, and z, which is 1/2 K Boltzmann times the temperature for each degree of freedom. So our kinetic energy is just going to be 3/2 Boltzmann constant times the temperature for our 3 translational degrees of freedom. We're not worried, by definition on this problem, we're not worried about the vibrational mode. So that's purely translational kinetic energy, 3/2 K Boltzmann times temperature. Problem number 15. The relation PV equals nRT holds for all ideal gases. The additional relation PV to the gamma holds for an adiabatic process. The figure below shows 2 curves. One is an adiabat and one is an isotherm. Each starts at the same temperature, pressure, and volume. Same pressure and volume. Which statement is correct? Note that alpha is proportional to. I'm going to think about that.